we're going to take a look at gases. Ultimately, the very first section of this is going to be the most important part as far as your final goes. We'll then kind of push into some relationships within gases. Not very important for the final. If you have to take 151 or just 151, they'll talk about gases a lot more in detail, and you'll go through a lot more math and all sorts of weird, crazy conversions. You don't need to stress as much about that now. But we will look at some of those relationships so you can kind of get a feel for what's going to happen in those classes. Okay? So, starting off, we want to take a look at some of the properties of gases. Okay? Your textbook lists 5. I think there's really only 4 because they kind of doubled down on 2 of those properties. Okay? Gases have a variable shape and volume. That means that they will fill whatever container is trying to hold them. Whereas you take a look at a solid or a liquid, they'll only fill up to their volume. But since gases don't really have a volume, they'll fill whatever volume they're in. Okay? They will expand and compress uniformly, okay, which is kind of an interesting idea. So when we push down on our gases, they will all adjust equally to account for that smaller space. If we give them more space, all particles within that will equally adjust to that space. We don't get weird shifts, only part of it does this, part of it does that. Okay? That said, can we come up with exceptions to this? Absolutely. Those exceptions make life and the mathematics behind this absolutely gnarly difficult. Is that something you would ever be expected to work with? If you moved into physical chemistry in 3 or 4 years, sure. Okay? And even then, it gives most people heart attacks. Okay? It's a ridiculous amount of math and all sorts of nonsense. Okay? I didn't say that about physical chemists. Physical chemists are great people. What we're looking at in these cases are ideal gases. Okay? So we want to treat them as a standard set. We're going to make some assumptions to simplify how we approach these things. And that's one of the things that we have to keep in mind when we deal with our gases. Okay? They have a very low density. Now they're just standard observation. Does it make sense for them to have a low density? Okay, what's the distance between any 2 atoms in a gas? Big or small? Really, really big. So within a given volume, we're going to have very few atoms within it, which means we have very small mass. So the mass to volume relationship, very small relationship. So we get small densities. Okay? Whereas if we move to, say, a solid or a liquid, what's the distance between atoms in those cases? Much, much smaller. So within a given volume, we can shove in a whole lot more particles. The mass to volume ratio now goes up. Okay? And then the last thing, which is kind of the same as 2, is that gases will mix uniformly with other gases in the same container. Okay? Which is kind of an interesting statement to make. What we're saying is that as long as that particle is a gas, it will act the same as any other particle. Okay, does that really make a lot of physical sense? Let's take a look at an example here. What happens if we take hydrogen gas? What's its formula? H2, so we'll go ahead and show it as the Lewis structure. And if we take a look at iodine gas, its formula is I2. Again, look at the Lewis structure. Would we expect these 2 molecules to interact the exact same way? Okay, according to our rules, yeah. Okay, according to what we would expect of these, would we expect them to act the same? What's the difference between hydrogen and iodine? What was that? Interesting idea, looking at charge. Not a bad idea, except those would be for the ions. We're looking at the molecule, hydrogen and iodine. Hydrogen in H2 will have a 0 oxidation state or a 0 charge. Iodine will have a 0 charge in I2. Different protons and neutrons, I'd take that a step further. What else is different? Not just protons and neutrons, but the electrons. What does a differing number of electrons do to our molecule? It does change the properties. It also changes the size. If we take a look at hydrogen, sure, there's its size, nice and happy. If we take a look at iodine, would we expect these two molecules to have the same interactions or the same potential for interactions? No. Iodine has a much larger surface area, which means larger surface area, more potential for interactions. Okay? So we could very well predict that they would be different. Okay? Do we want to go with that difference? No. Why not? Because that makes life hell when it comes to the mathematics, and it's already bad enough. Okay? So what we go through and do is when we look at a molecule of hydrogen and a molecule of iodine, when we put them into the gas phase, we say they are exactly the same. There is no difference in how they interact with other particles. Okay? So it's a pretty big approximation that we will look at an example in a second that actually seems to hold relatively true when we look at our gases. Okay? Last thing that we can think about here is that gases will exert a force on whatever container that holds them. Okay? Which might be why gases were first discussed. Okay, well, what is that force? Okay, is there a force? I mean, I walk through the air and there's nothing pushing me. I'm doing just fine. Okay, for those of you that didn't turn around, I was dancing. Okay. There's nothing pushing me. I don't feel any force. I'm moving just fine through the air. What happens if I go outside? Probably still just fine. What happens when we get one of our haboob monsoon wind things? Okay. Now I get wind pushing at me. I don't know if any of you have had to try to bike through one of those, but it's really not pleasant. Okay. That wind definitely pushes against you and prevents you from moving. Well, if that's preventing motion, that is a force. I can't see that force. All of a sudden, wind comes along, whoosh, there I'm gone. Okay? That invisible force is probably what started a lot of people actually looking into gases, trying to figure out their properties and understand something about them based on that invisible force. Okay? As we see on that this next slide, that force is what we refer to as pressure. Okay, so that's the end of that slide. So let's go back up to the beginning. We look at statement 1. Okay, gases have a variable shape and volume, and we kind of mix this with some of the other rules. With even 4, they'll always mix uniformly. When we looked at hydrogen and iodine, okay, we said there was a very big difference in size. Iodine has a lot more electrons, much, much larger than it. Okay? Well, for all of these rules to work, one of our big assumptions that we're making on this is that each particle of gas does not have a volume. Okay? Why is that important? Well, if I put a particle of gas into this empty space, okay, on its own, not a big deal. What volume does it have to be able to move through? So if we take a look at a square, draw it in our upper right-hand corner here. Square, 2 inches on a side, and I put my particle in there. What volume does that particle have to move through? 4 square inches. Okay? What happens if I add a second particle? What volume does it have to move through? 4 square inches. Okay? And when we look at a gas, the distance between those particles is really, really far away from each other, so we don't really worry about it. Okay? But what happens if we now change our assumptions a little bit? Instead of it being a really small particle, now let's make it a really big particle. What's the volume that those 2 particles have to move through? Can that blue circle ever exist where that red circle is located? No. What does that mean? Does it have 4 square inches anymore? It cannot be at that space. We have lost volume by putting our particles into that. So as soon as I put more than one particle into anything I want to look at, my volume changes. And it's going to change proportional to the size of that particle. Oh my gosh, I now put in 3 particles. What happens? Now it changes even more. Every time I put in a new particle, I have to calculate a new volume and do a new calculation and new interpretation. That is a lot of bloody effort. So what do we do instead? We go through and we say our particles have no volume, which means when we put them into our space, we say that they are effectively these tiny little dots. So that, yes, technically, that blue dot cannot exist where that red dot is. But how much of a loss in volume is that? Relatively small. So now instead of it being in 4 inches squared, or 4 square inches, whatever it is, it's now 3.9999999 inches squared. As far as significant digits go, what's our area? Still 4. Okay? It's that approximation that allows us to do a lot of simplifications with our overall mathematics and allows us to manipulate these things. Does that approximation make sense? Okay? Well, what happens when I put a single particle into a large volume? Okay? Does the volume change much? No, why not? Let's take that single particle and let's put that into a 2-liter bottle. Got a rough idea on our 2-liter bottles, right? How much volume has been removed by putting that single particle there? Something infinitely tiny. So when we're looking at our gases, one of the things that we've said is the gases never really touch each other. They're always really far away. That's how we could get into the gas phase. When we're at a solid, we put them close to each other. But gas phase, they're really far away. Okay, well, if they're really far away from each other, they effectively don't interact all that much. That simplifies our calculations. We can now say that each particle has no volume. Okay, and this only works for particles that are in what phase? Gas. The gas phase, okay, which will become relevant when we talk about solutions next week. Okay? So what's the big approximation that we can come off of this, or the big conclusion that we can make from this? The big hint, it's in red box. Okay? 1 mole of a gas will equal 22.4 liters. What if it's a hydrogen gas? What's the volume? 22.4. What if it's iodine? Freaking massive, big old iodine. If I take a mole of those particles, what's the volume? 22.4 liters. It does not matter how massive my particle is, it will always occupy that same volume. And that is because we've stated that we are looking at an ideal gas. Okay? And remember, this works for gases and only gases. Yes?
I forgot. Why do the particles of gas always stay away from each other? Like, why do they spread out?
So one of the things that we'll look at is they don't necessarily always stay away from each other. They will constantly move throughout the solution. But whenever they interact, they completely bounce away from each other elastically. Okay? So there's no loss of energy. I thought that was on this slide, but apparently not. We'll talk about more of the rules on why that we're looking at ideal situations in a little bit. At this point, we really just wanted to cover this rule, or 1 mole of gas. But we will see on what other approximations that we're making. And ultimately, it's an approximation. We're guessing. Okay? And the reason we're guessing is because otherwise it becomes way too difficult. Okay?
So just don't think about it.
Kind of, yeah. Think about it like you would think about the meaning of life. Okay? So it's a good thing to every once in a while think about and come across and ponder about, but it's not something you should spend your whole life struggling with. Okay? Any other questions with what's in that red box? What the heck is STP? Which is a ridiculously good question. Ask an engineer that. Okay? Ask a mechanical engineer. Ask a material engineer. Ask a chemist. Ask a physical chemist. Ask a biologist. Fun thing about asking all those different people, what do they tell you STP is? Something different. It's really freaking obnoxiously stupid. What does STP stand for? Standard temperature and pressure. What is standard? Well, it depends whatever I'm working with. That's my standard. Okay? That's the way it works. Okay? When we're looking at chemistry, our standard temperature is? Room temperature is not a bad guess. Turns out to be 0 degrees Celsius. Okay. Why? Because that's what we decided. That's what it's going to be. What about the pressure? What's our standard pressure? Okay. Pressure one is actually a little bit better to work with. Okay. Where are most of our experiments done? Okay, so first off, let's think about it this way. We haven't even quite talked about pressure that much. What happens to the pressure as we move from low elevations to high elevations? Does it change? Yes, it does. Where are most people located? At low elevations, ultimately at sea level. We could go below sea level, but not very easy to run experiments under sea level. Okay? So we're usually running right about at sea level. So what we decide is our standard pressure is the pressure found at sea level. Okay? And when we get into pressure, we'll find that there are varying units for that. Ultimately, what we're looking at here is 1 atmosphere, okay? Or atmospheric pressure at sea level. Okay? The rest of those all kind of go back to that, and we'll come back to those kind of conclusions when we go through and look at our ideal gas rules. Okay? So our force now is our pressure. So we want to come up with some idea on what's happening with pressure. But before we really get into pressure, I want to do one extra thing. What's in that red box? A conversion factor, which means more dimensional analysis. Okay? Yep. You're not going to get rid of it. Okay? This is extremely important for your final exam. Being able to use that conversion factor, the relationship between the moles and the volume for an individual gas. So let's take a look at a couple examples here. Okay, let's start with our first one, relatively simple. How many liters are needed to hold 2 grams of hydrogen gas at standard temperature and pressure? Where do we start our problem? Excuse me. Okay, I heard a couple answers there, and I can kind of accept them all. But the way we've been starting is saying, where we end, liters. And I still don't quite accept just liters. Liters of hydrogen gas. We need that H2 in there. And then we could go back with where the other people were suggesting we start. With what we actually start with. What do we start with? 2.0 grams. Man, maybe I should have had lunch. What is our formula for hydrogen gas? Why is it H2 and not H? It's a diatomic element. Okay, I just want to make sure we hit that. So, what do we do now for our dimensional analysis? Take a look at your units. Does grams of H2 equal liters of H2? No. What do we have to do? We need to minimally get rid of grams of H2. What do we want for our final answer? Liters of H2. Do we have a relationship between the grams and liters? No. Oh, shoot. So we bust out the eraser and get that out of there. So now we can shotgun method. What can we convert grams to? Okay. Some of you are saying moles, which I like. That is where we want to jump to. Why might we jump to moles and not say something like AMUs or something else? How do we get liters? From moles. It depends on the conversion factor that allows us to progress forwards. If we converted to AMUs, there's not anything necessarily wrong with that, except we would find that we don't have the conversion factor that gets me to liters, which means I'd have to go back to grams and undo that calculation. Okay? So we want to get to moles. Oh, that's an eraser. Let's try that again. Moles of H2. What is the relationship between grams and moles? Where is that relationship found? The periodic table. Okay, so we go to the periodic table and we want to figure out our molecular weight for hydrogen. What is our molecular weight for hydrogen? Why did you say 2? A hydrogen atom is 1.2 0.01. How many hydrogen atoms are in the formula of H2? 2. We must multiply by 2. Where does that number go? I want to get a little bit more detail than bottom. In front of the grams. I didn't actually hear, apparently I heard one person say the correct thing and just assumed everybody else said the same thing. What else was the other answers? Nice, fair enough. It should go in front of the gram unit. Remember, the numbers on our periodic table are ultimately grams in 1 mole. Okay? What units do we have now? Mole, I'm not going to quite accept that. Thank you. Moles of H2. Is moles of H2 our answer? No. So what do we have to do? Conversion. What do we want on the bottom? Moles H2. What do we want on top? Liters of H2. So again, we go through and think, do we have a relationship between the moles of a substance and the liters of a substance? Yes, and in particular, that we get a little bit more specific, do we have a relationship between the moles of a gas and the liters of a gas? Yes. What is that relationship? 1 mole equals 22. Well, that's a good thing to put the numbers in front of the units that we're talking about, right? 1 mole is 22.4 liters. You notice it is very simple to put the numbers in the wrong spot. That's why you track the units. Make sure your number shows up in front of the appropriate unit. Okay? What would our units be now? Liters of hydrogen. Is that what we want for our answer? Yes, which means stop converting, put it into your calculator. To go through and enter this into the calculator, what I would go through and do is take everything in the numerator, multiply it out. So we get 2 times 22.4. Then I would take everything in the denominator, multiply it out. So 2 times our 22.4 gets us what, 44.8? Divided by, or sorry, over 2.02. I haven't done any division yet. It's all nice and simple multiplication. Now I can do my division. I'll do 44.8 divided by our 2.02, and we should get our final answer. Oh, that was kind of a boring question, wasn't it? Get roughly 22.4, right? Know-it-alls. That's true. 22.18 liters of H2O. Does that number make sense? Should it come out to be roughly the exact same as our molar volume? Why? We could look at it mathematically. Let's look at it physically. 2 grams of H2O is roughly how many moles of H2O? 1 mole of H2O. So we take 1 mole of H2O, or H2O,
Yeah.
H2, 1 mole of H2, that should be 22.4 liters. That's what that conversion factor meant. Why did it shift a little bit off of being exactly that answer? It's 2.02. It's not exactly 2. Okay? Questions about that? That is one that you should absolutely be able to do, and you fully should expect to see that on your final exam. Let's make it more difficult. Well, did you have questions about that? Please say no, because I already deleted it all. We'll take that as a no. How many liters of hydrogen are produced from the reaction of 0.165 grams of aluminum metal with dilute hydrochloric acid? Oof. Okay, this is wicked. Now, instead of dealing with just one species, I've got officially 4 things in this equation. Okay, so I'm going to have to go through and process this very, very carefully. Where do I want to start? What do I want to end with? What do I want to end with? Liters of hydrogen gas. What do I start with? Whoops. I even wrote the question. How come I don't know the numbers? 6.5 grams. Thank you. We need the complete unit of aluminum. Okay. First thing that should be a red flag for you. Well, there are a couple things that should be red flags. Number one, you'll notice that we see an equation. Okay. We could see that it's not balanced, which means we'll have to address that further. Okay. Equation could be a red herring, but if it's shown, it's probably meaning that you need to use it. Do we have to use it? What do we start with? Grams of aluminum. What do we want to end with? Liters of hydrogen. Yes, we get a unit change, grams to liters, but we also get a substance change, aluminum to hydrogen. The only way to change substances is the mole ratio found in the balanced equation. Okay? So up to you if you want to decide to balance it now or not. What do you guys think? Balance now?
Yes.
Okay. Can I fake my memory? 2, 3. Yes? 6, 6. Yes. Cool. Look at that. Done it a few times. Okay? You should be going through and being able to balance those relatively quickly. Okay? So, we've got that balanced. If this would show your work, hey, you got some partial credit. Remember, your final is not partial credit. Okay? It's just multiple choice. So you got to be very careful with how you approach these. So, let's go back to our conversion. Is grams of aluminum equal to liters of hydrogen? No. Which means we have to convert. What do we want to get rid of? Grams of aluminum. Ideally, we get liters of hydrogen. Do we have a way to relate two independent units and two independent substances? No. So we would, of course, erase that and now go, okay, what can I do? Why convert to moles? Mole to mole ratio gets me through my balanced equation. I can convert my substance. So what I want to do is convert to moles. So I'm going to write moles, hydrogen, right? That's what I want. Why not? Okay, I don't have a relationship between the grams of a substance and the moles of a different substance. Okay? Make sure that your units make sense. Where do we find that relationship? From the periodic table. What's the periodic table tell us? What? Oh, maybe you said the 2 in front and I didn't hear it. 26.98 grams of aluminum per 1 mole of aluminum. Put the numbers in with the appropriate unit. What units do we have now? Moles of aluminum. Is that our answer? No. What do we want? We want liters of hydrogen. So we got to get rid of our moles of aluminum. What should we convert to? Moles of hydrogen. We could convert to other things as well. Why do we convert to moles of hydrogen? Keep in mind your target. Your target is liters of hydrogen. We can't convert the moles into liters with a different substance. But if I convert moles into moles of hydrogen, my unit, the mole, may not be getting me closer, but my substance is now closer. Okay, so you have to keep in mind both the unit and your substance and try and do something to get you closer towards that. What is the relationship between those two? I'm not going to accept 2 to 3 or even 3 to 2. Come on, what's the issue with that? You just gave me numbers. I don't want numbers. 2 what? 2 moles of aluminum. Why do I want the unit in that statement?
So you don't mess up the number.
Where does the 2 go? With the moles of aluminum. 2 moles of aluminum to 3 what? Moles of hydrogen. The 3 must go with our hydrogen. Okay, what units do we have now? Moles of hydrogen. We got our substance fixed over, but we don't have our unit fixed. Okay, so we have to do yet another conversion factor. Do I finally have a relationship between the moles and volume? Yes. What is that relationship? 22, thank you for including the unit on that. 22.4 liters is 1 mole of our hydrogen. Track your units after we've done yet another conversion. Moles of hydrogen cancel. What units do we have? Liters of hydrogen. What answer did we want? What do we do now? Bust out the calculator and start punching it in. How to process it in the calculator. Okay, again, this is how I would approach it, up to you. Take everything in the numerator, 0.165 times 3 times 22.4, I don't know why I had to pause on that, divided by everything in our numerator, denominator, whatever that thing is, 26.98 times 2 times 1. Oh, geez. I can't do that one in my head. I need some help. Is that the final answer? That's the denominator? No, I don't believe that. Numerator, maybe.
It's 11.088.
I want
53.96.
88.
0.088. And then the bottom is 53.96.
I've done all of our multiplication. Now we'll go through and do my division. 11.088 divided by 53.96. Really shouldn't be that difficult for me to write that down. But okay. We now have an answer. We can go back, look at our units. Yes, our units match up. Nothing seems odd in there. Okay, and we've got our final answer. Look at me, I didn't do it. Okay. Questions about that? Extremely advanced question as far as this material goes. If you can get through these types of conversions, you should be set for any of the conversion questions that are going to get thrown at you on the exam. Okay? So, now back into kind of the general stuff. We can take a break away from all the numbers and just kind of think about things. Okay? Because thinking is so much easier in numbers, right? Atmospheric pressure. Okay? So what someone went through and started to manipulate was say, okay, we've got this wind, there's some weird invisible force pushing against me. I want to try and come up with some way to measure it. Okay? And this is a really bad way to segue into it because I don't think it really makes any sense, but close enough. Someone, for some reason, took a test tube, filled it with mercury, and said, hey, wouldn't this be fun if I flipped this upside down in a bunch of mercury and saw what happened? Okay, what would you think would happen? All right. Let's get rid of the tub of mercury. Let's just take that test tube. Let's get rid of mercury, too. Let's make it a little bit easier. Let's take water. Test tube full of water. Turn it upside down. Put it on the counter. What happens? All of the water goes rushing out. Well, that was kind of boring. I just made a mess. Let's fill up that tube of water. And now let's take a beaker, fill that with water, and put the tube upside down into the beaker of water. Interesting. Some water stays in the tube. Why would it do that? Okay. Well, let's take a look at kind of the image on what's happening. In our first case, what happened? Our stuff ran out of the liquid. For it to run out of the tube, it had to go out. And if we put it into now our beaker with more liquid, not only does it go out, but what happens to the volume in the beaker? The beaker must go up. Okay. If for some reason it stops dropping out of the tube, there has to be some counteracting force to keep it up in the tube. Well, what is that counteracting force? Because this is just a liquid. I'm not pushing on that. In fact, if we tried to push on the liquid, it would just make a mess. What is pushing on that liquid? That is our magic gas force. Okay? That magic gas force we have defined as atmospheric pressure. The person who allegedly first did this, sorry, I forgot their name, did this and then monitored it over several days and noticed that the level of the mercury changed. particularly as the weather changed. All of a sudden the mercury was moving up and down all over the place. Okay? But it never completely left. What they observed was the pressure, our atmospheric pressure, changing with the weather patterns. What they've come up with now is a way to measure pressure. Okay? So now let's attempt to quantify this. Okay? How could we quantify that pressure? Well, we said there's mercury up in this tube. We could measure how high up the tube the mercury was. Okay? So at a given instant, I could say it was 60 inches of mercury. Oh, and the next day it dropped to 59 inches of mercury, and the next day it went up to 62. I now have a way of correlating that external pressure pushing on the mercury to the height of that tube. Okay? What we just created, or what was just invented there, was the first units for pressure. Okay? Kind of neat. Looking at just the distance within a tube. Okay? Mercury just happened to be the most consistent, has a very low vapor pressure, which we'll talk about in a second, make things a little bit easier to work with. Okay? So that's where our pressure is coming from. All gases have some energy that they are now exerting on their environment, or the container that holds them. Okay? In the case of our atmospheric pressure, the container that is holding it is the planet. Okay? And that gas is now pushing down on every surface, including liquids. And because our gases always move uniformly, when our gas particles push down on the right side of the liquid, it's also pushing down on the left side of the liquid. So we don't see our liquid shift oddly within this. It uniformly is pushed down equally at all individual positions. Good way to observe what we saw with our gases. They are uniformly pushing everything. Okay? So we now have a way to measure this pressure, this force. How hard does it push mercury up a tube? Okay? Fortunately, it's not quite as simple as that may have sounded. It'll get a little bit more complex, but we'll look at that more complex thing in just a second. Unless you have questions. Do you have questions about that? Okay. The next thing is looking at the vapor pressure. Why did they use mercury? Okay. It has to do with vapor pressure. Mercury is a liquid, and that's one of the things we need to have it move through the tube. If it was a solid, it's just going to sit in there. It's kind of boring. Okay? It has to be a liquid. Mercury, if we put a container of mercury out on the counter and leave it alone, what happens to the volume of the mercury? It stays the same. Okay? If we had decided to do this experiment with water, put that container of water out on the counter, what happens to water? It evaporates. It disappears. Why is it disappearing? It's disappearing or evaporating because it has a relatively high vapor pressure. Okay? What's happening with vapor pressure is that all liquids, okay, are being held as liquids. So when we move from a solid to a liquid, what we've done is broke all of those individual molecules away from each other. Okay? Well, we put in all of that effort, but they didn't all completely make it away from each other. Why not? Because the atmosphere said, F you, I'm going to hold it down a little bit. Okay? So atmosphere is holding on to each of those liquids, preventing them from going completely into a gas. But the atmosphere doesn't do quite a perfect job doing that, and so every once in a while, one of those liquid molecules pops up and says, yay, I'm a gas, completely free. Okay? What happens to that now? Okay? In the case of our open container, what's moving over the top of our container? Gases or air. Okay, so our little water molecule pops up into the air, gets caught up by the air, and then moves on. Okay? Well, now the water says, well, there was a seat up there. Well, fill that seat. Pops another water molecule up into it. Air comes along, sweeps it away. So water keeps saying, got to fill that seat, got to fill that seat. So it keeps launching little water molecules up into that spot and keeps sweeping them away. Okay? Or air keeps sweeping them away. What if we take that same container of water, and instead of leaving it open, thank you, I close it. What happens to the water level now? Stays the same. Why does it stay the same? Okay. that seat is now permanently filled by that gas molecule. Water molecule jumps up into the gas phase. There's no air to sweep it off the top. So that means water says, okay, my seat's taken, I can't push any more molecules up, and it stays at that volume. Okay? So what we're looking at is, at vapor pressure, is the natural tendency of most liquids to jump up into the gas state. Some molecules have a very high ability to do this. Some molecules have a very low ability to do it. Mercury's ability is horrible, which is why it's fantastic for measuring pressure. Because I can leave that container of mercury out on the counter, and I don't have to worry about it evaporating off. Because eventually, if it evaporates off, what happens to all the liquid in the beaker? Or the tube? And it's going to continue to fall out. Okay? So that's why mercury was first used, because it's really good as far as that goes. Could we potentially look at the reverse of this? Let's say instead of trying to take our liquid and put it up into the gas, we take a gas and we want to dissolve it into the liquid. Do we ever see that happen? Never do that in the real world, right? You're all pretty healthy, so I can't really pick on anybody right now. Go to get a soda. What happens with your soda? Kind of bubbly and fizzly. It's all kind of fun. Ooh. What's that bubbly and fizzly coming from? CO2. What is CO2? A gas. Why the heck is it coming out of your water? Okay, we forced CO2 into the soda. How did we get the CO2 to get into that water solution? We forced it in, or we used enough pressure of CO2 and forced it into the water solution. Okay, now what happens when we open up our container? CO2 says, I'm free, and immediately jumps out of the water, and we get this big fizziness. Okay, and then eventually it takes a little longer to get the rest of the CO2 out of that solution. And so when we first open up our soda, it stays fizzy for a little while. Okay? So to get that carbonation, to get that gas into our solution, we have to put in a massive amount of pressure. There's something else that we could do to adjust that. Okay, anybody used cans of soda or heard stories about this, say in Arizona, middle of the desert?
Oh, yeah. Great for target practice.
Different purpose or reasoning, probably more fun. If you take your can of soda or your option, which I'm not allowed to say for recording purposes, and let's say, oh, I forgot and I left that in the car. It explodes. Why would it explode? What does the heat do? The heat causes the CO2 to say, I don't want to be in this solution. So it is frantically trying to claw its way out of the solution to get up into the gas phase. Okay? In a closed container, that's not that big of a deal until eventually what happens, that the pressure builds up from our gas pushing out so much that the container says, I'm tired of this, I'm tired of the pressure, and blows up. And what happens? You now have this massive, nasty, sticky mess all over your car. And in your case, if the police pulled you over, they'd have a real fun talk with you too. Okay? Probably for a very long time too. It's going to take a while to get that out of the car. Okay? What happens if we cool it down? Okay? So when you're talking about freezing containers, that's a separate issue. I want to look more at the gas. Okay? If we heat it up and the gas wants to jump out, what's going to happen when we cool it down? The gas can stay in. So if we want to try and put more CO2 into our carbonated beverage, what do we need to do? Really high pressures and keep it cold. Okay? So those are going to adjust our vapor pressures. There may have been a question. Was that a question? No? Okay. Was there a question? I thought I saw a hand. I'm guessing you're just stretching. Okay? So back to our units of pressure. Really don't want to spend a lot of time with this just because I personally find it obnoxious. Okay? When it comes to pressure, this observation of this invisible force was something that was made probably universally around the world, all probably at different times. And when we looked at our initial conversation abilities, a person in New Zealand couldn't talk to a person in the US, couldn't talk to a person in England, or really in Europe or in Asia. And so they each had their own way of measuring this pressure phenomenon. Okay? Which on its own isn't bad, because then we all get together once we can actually talk and communicate with each other. We sit down like normal people and we say, okay, this is ridiculous. We have way too many different units. Let's come up with a standard unit. And we know just how well it works to get everybody to agree to one thing. And what ends up happening, we have a crap ton of units when it comes to possible units for pressure. Okay? So if you move into 151, you will be expected to have to convert between all of these stupid units depending on what the question asks for. So not only do you have to know what atmospheres are, you have to know what inches of mercury are. And how do you convert between atmospheres and inches of mercury? Okay? How do you convert between inches of mercury and PSIs? What is PSI?
Pressure per square inch.
Pounds per square inch. Okay? Same thing. Pascals. Okay? kPa, kilopascals, that last one. What is that one about? Pascal did the most research in gases. He invented his own pressure unit named after himself. Awesome guy. Thank you very much for accepting one of the other units. Okay? Each of these have their own particular purposes and reasons why we use them in different situations. Okay? Depending on what the problem is asking, you may be asked to convert between these. So how do we convert between atmospheres and centimeters mercury?
Is it all the same? Like atmosphere is equal to
What we're looking at here is our standard pressure at 1 atmosphere, or in the units of atmospheres, our standard pressure is 1. Guess which one of these I have memorized for standard pressure? 1 atmosphere, yeah. Like, go figure, right? Okay. What happens if I now want to convert atmospheres into inches mercury? Well, this 29.9 inches mercury is standard pressure. What did we say 1 atmosphere was? Standard pressure. So if I want to convert atmospheres into inches mercury, 1 atmosphere equals 29.9 inches of mercury. What if I want to convert centimeters of mercury to PSI? 76 centimeters of mercury equals 14.7 PSI. That's the intent of using this chart. You're given a ton of different conversion factors here, and I'm sure this is barely a handful of them. Okay? Yeah?
Do we have to memorize?
You do not have to memorize these. This is here as kind of a warning, maybe, of how I personally dislike pressure as a unit system. Even when you move into more advanced classes, they will probably center around the atmosphere unit. Okay? Probably because they're just as lazy as I am and can memorize the standard pressure being 1 atmosphere. Okay? So that will be your standard unit when it comes to pressure. All the other ones, depending on who you're talking to or where they're coming from, you might hear different things. Okay? So you should be able to convert between any one of these. As you were kind of alluding to or asking about, and I kind of alluded to, these conversions do not show up on the exam because you won't need to use them on the exam. Okay? So now into kind of the interesting things. I actually had demonstrations, sort of demonstrations for this, but then we only got 5 minutes, so it's not like much is going to happen. Ideal gases. So what we'd be looking at is an ideal relationship between individual gases. Okay? So we've got some assumptions that go behind how we're going to simplify our calculations and manipulate these things. We've talked about a lot of these. Gases are made up of tiny molecules, so tiny that when we actually evaluate the mathematics behind them, they have no volume. Okay? So that's one of our big assumptions. They move in random directions. Okay? Molecules do not have a mind of their own. They will go wherever they want, whenever they want. But one of our assumptions as well is that they're going to move in straight lines. Okay? Why is that easier to work with? Well, if you're trying to predict the motion of anything, it's a lot easier if you tell you can only go backwards and forward, or you can only go in this straight line, you can't turn on me. Okay? It just makes calculations a little bit easier to work with. Other things, they have no attraction for one another, okay? Which works in most cases for gases. If we go ahead and put any particles near each other in a gas, we say they have tons of space. They're really far away from each other. Well, if they're really far away from each other, what are the odds they're going to interact ever? Really, really limited. Okay? Even when they do get close enough where they could interact, we further simplify and say that they hit and bounce without losing energy. So whatever energy they started with when they hit is the same energy that they leave with. What's going to change? The direction. Okay, so they will bounce and change directions, again, only in a straight line.
So does that mean they have no atomic charge?
In the ideal gas calculations, yes. We look at no charge. There is no, and that doesn't mean the atoms aren't charged. That means we do not consider the charge contributing to the properties of the gas.
So they don't, okay.
Okay? Which is a very kind of odd statement, but we're just saying that those things don't happen. Okay? And depending on what gas we're working with, our analogy could be really, really bad. Okay? The last thing here, if we look at kinetic energy, so the amount of motion that they have, is directly proportional to temperature. Okay? What does that mean? If I increase the temperature, what does that do to the motion? It increases the motion. Okay? So that's all that statement is really saying. So when we jump the temperature, we increase motion, it moves around more. Okay? So from these kind of assumptions, we can come up with some variables that relate these. So if we now have a balloon that we can work with, what did I just do? I put air into it, which means I changed what? I didn't change the volume. The volume changed based on the balloon. What did I put into it? Volume and pressure. I put in gas. I put in more gas molecules. How do we measure the number of things? Moles. I increased the number of moles within this. Okay? What's our symbol for moles? We typically write it as MOL. Anybody see MOL up there? No. Okay? What is our symbol for moles as far as gas laws go? N is our number of moles. Okay? What happened to the volume when I put that more moles into it? The volume increased. So what we said is that when I increase the number of moles, what happens to the volume? Volume increases. There is a direct relationship between these. So I could set up an equation. N will equal my volume. Does it go directly with it? Turns out not exactly. So we have to account for some random scaling factor. That scaling factor we'll put in here as an R, some constant. What happened to the pressure? All right, so let's say I could hold the volume here, not let it grow any larger, and I continued to blow into it. The pressure is also going to increase. So what we're now saying is that our number of moles roughly equivalent to our pressure. Again, through some scaling factor. What happens with our other situations? What happens to the volume? Let's do it this way. What happens to the pressure if I decrease the volume? If I can take this balloon and now shrink it down, what happens to the pressure? It increases. So what's the relationship? I shrink the volume and my pressure went up. Is that a direct relationship?
You're pushing the particles closer together.
Yep. Still goes back to our pressure. If I decrease the volume, what happens to the pressure? The pressure goes up. Remember, if I continue to kind of shrink this down, eventually what's going to happen? It'll pop. Okay? Yeah, I'm not going to shrink it that much. I don't want it blown up in my face. So what we're saying is that there is an indirect relationship between volume and pressure. Okay? Again, through some scaling factor, some constant. What happens with our volume and temperature? If we increase the temperature of this, what happens to our volume? Also starts to increase. So we're seeing a whole bunch of different relationships that are coming out of this, and what we can end up doing is combining all of those individual relationships into this overall equation. Right? You may have heard chemists refer to this before by its abbreviated name, Fidner. Right? We're looking at the ideal gas law. Pressure times volume will equal moles times some constant times temperature. This is a massively important equation, largely all because of that R value. Why is that R value important? If I look at a gas at conditions A, my R will equal my pressure at those conditions, my volume at those conditions, my moles at those conditions, and my temperature at those conditions. What happens if I change the conditions? What's going to change about my R value? Absolutely nothing. Why not? Because R is constant. I can use that information to now set two separate conditions equal to each other. Okay? And it could go through, and I could now go through and solve all sorts of different problems along those lines. Okay? The last thing that I'll end with here, I know it's kind of fast, is what is that R constant? Okay? It is usually 0.0821 atmospheres times liters per mole times Kelvin. Why is that important? What are the units? Atmospheres, liters, moles, and Kelvin. What units of pressure should we use? Atmospheres. What units of volume should we use? What units for temperature? Kelvin. What if your temperature is given in degrees Celsius? You have to convert it to Kelvin before you can use this gas constant. What if you use degrees Celsius a lot? You can invent a new gas constant by converting Kelvin into degrees Celsius. 9 times out of 10, this is the conversion factor you will end up using. Again, not on the final. Okay? You will see some post-lab questions on it, manipulating and dealing with these kind of inner conversions back and forth. You are responsible for having seen it, so we're going to talk about it and doctors about it. I would recommend you look at the rest of the slides, but they aren't super important. They're kind of summary topics. If you've got any questions, you can talk to me after class or email.